Hey guys, in this video we'll apply the full concept of work, which is to say we'll apply the work energy theorem as well as the formula we learned for work that includes forces. This one says a crate is pulled by a force parallel to the incline of a rough incline. The crate has an initial speed shown in the figure below. The crate is pulled a distance of 7.06 meters on the incline by a 150 Newton force. The acceleration of gravity is 9.8 meters per second squared. Here's the sketch, and then the question is, what is the change in kinetic energy of the crate? Because it is a rough incline, we have friction and we have the coefficient. Okay, we learned that the net work is equal to the change in kinetic energy, as per the work energy theorem. Also, we learned that the net work is equal to the work done by non-conservative conservative forces, let's start with conservative, plus the work done by non-conservative forces. In other words, we have to find all the forces acting on the object and find the work done by those forces. Okay. Also, we learned that the net work is equal to the net force times the distance times the cosine of an angle. Okay, let's go back to this one. We need to find the work done by conservative forces and non-conservative forces. In other words, we need to know information about the forces. To make this video shorter, I have my given information based on the problem, and here's my free body diagram. I like to have the incline just to have as a reference, and what I did is I changed my coordinate system so that the normal force, frictional force, and applied force match x and y axis. As you can see, the weight of the object, weight is equal to mass times gravitational acceleration, does not fit either in the y or x direction. That's because it has components. Okay, so the component of the weight along the y direction will go like this, and then the component of the weight along the x direction will go like that. So I'm going to call this one mgx, as it is acting along the x direction, and this one I'll call mgy. There we go. My free body diagram with the components of the weight. Okay. Now let's think about what forces are doing work on the box. Well, of course, the applied force, because it's moving upward or up the incline. Friction, that's opposing motion. And if we were to remove this force applied, then the box would slide down the incline because of its weight. So normal force is not really doing work, but we're not going to take that into account. So we have these three forces. So then the net work will be equal to the work done by the applied force plus the work done by friction plus the work done by the gravitational force. I'm going to say gravity. Okay, we need to find those three, or these three forces. I will start with the work done by friction because I think that's the one that's going to take me the most time, and I think I'll split this video in two parts so you're more willing to watch the whole thing. Okay, let's start with the work done by friction. Okay, if you go back to this equation, this formula, the net work is equal to the net force times the displacement times the cosine of theta. So for one force, right, because we're not thinking about the net force, just one force, we can say the work done by friction is equal to the force of friction times the displacement times the cosine. I cannot say theta because theta in this case belongs to the incline. Don't forget that this theta, this angle, belongs to the force. Gives me information about the direction of this force. So because theta is taken, I need another Greek letter. I'm just going to call it alpha. You can use whatever Greek letter you want. I'm going to use alpha. Okay? Let's think about what that is. Well, force of friction is down the incline. The direction of motion, I'm going to trace it with this dotted line, is up the incline like that. So that means the angle between the head of my force vector for friction and the direction of motion is 180 degrees. And that makes sense because if you think about what type of work friction is doing, is negative work. And we know that the cosine of 180 degrees is -1. Therefore, the work done by friction is negative force of friction times displacement times -1. Well, the negative comes from the -1. Okay? Although this seems a very simple equation to solve, we were not given the force of friction. We have to use the general formula for force of friction. And that one says, I'm going to work on this side. Frictional force is equal to the coefficient of friction times the normal force. Okay, we don't have the normal force. It was not given to us. However, we have our free body diagram, and we can apply Newton's second law to find the normal force, to find an equation for the normal force. So let's apply Newton's second law. Notice how normal force is acting along the y direction, and just as a formality, I'm going to make this positive, which means its pair, the pair for the normal force, would be the y component of the weight, and that will be negative. And then, just because we're here, this is positive direction. This one we know should be negative. And then this is also pointing down the incline, so this one will also be negative. Okay, so let's apply Newton's second law along the y direction. Just two forces. That's simple. So sum of the forces along the y is equal to normal force minus the y component of the weight. That's equal to 0. There's no acceleration along the y direction. We don't know what this is, mgy. However, I can see my right angle, and don't forget that this angle over here, that's going to be theta. That's my theta. Okay? Let's try that again so it's not all crammed. So this is theta. If you apply trigonometry, I want to know information about mgy based on my right triangle and my angle theta. Now this is theta in fact because this angle is based on the angle of the incline with a little bit of geometry. Okay, so this is the same angle as this. So based on this angle, I want to know information about the adjacent side. I know the mass of the block, so I can use the hypotenuse adjacent, meaning I can use the cosine. So cosine of theta is equal to the adjacent mgy divided by mg. I solve for mgy. That's equal to mg cosine of theta. So now I can say that the normal force minus mg cosine of theta is equal to 0. I solve for normal force. Normal force is equal to mg cosine theta. Therefore, my frictional force is going to be coefficient of friction times mg cosine theta. Now we can find the work done by the force of friction. Work done by force of friction is negative force of friction. And then I need to have the displacement. Normally we do that in an alphabetical order, or normally this shouldn't go at the end. So I'm going to include it in between gravitational acceleration and cosine theta. It wouldn't make a difference because it's a product, so the order doesn't matter. But just because that's the way I've always done it. So coefficient of friction times the mass times gravitational acceleration times displacement times the cosine of theta. I have all that information. That's all in my given. So then I'll have negative 0.337 times the mass, that's 10 kilos, times 9.8 meters per second squared. Displacement, that was 7.06 times the cosine of 35 degrees. That was my angle. After I plug that in, I use decimals. The work done by friction is negative 190.996 joules. And that's how we find the work done by friction.